Hey everyone. We'll be doing some integrals, definite and indefinite. We'll be doing some trig and others. So let's get right into the video. So for my first example, I'll have this type of an integral. And we should know that the integral of sine x dx, bounds don't matter. Let's just assume that this is an indefinite, just for now, is equal to negative cosine x plus c. So how do we determine this? Okay, so we can draw this out. So we have sine x, then we have cosine x, then we have negative sine x, and then we have negative cosine x. Okay, so in order to get from sine x to take the integral of sine x, we'll have to go backwards. And when we go, wait, we have to go backwards. And when we go backwards, we approach negative cosine x. When we go backwards from negative cosine x, we approach negative sine x, because the integral of negative cosine x dx is just negative sine x plus c. In order to go from negative sine x to cosine x, you just go backwards, and from cosine x, you just take the integral of that to get to sine x. So the top part is all about integrals. And then the bottom is going to be about derivatives. So for derivatives, it's going to be the opposite. In order to get from sine x, in order to take the derivative of sine x, we'd have to go one forward and go to cosine x. In order to take the derivative of cosine x, we'd have to go one forward and take the derivative of cosine x, go one forward on this scale, and you go to negative sine x. Take the derivative of that, it's negative cosine x, and take the derivative of that, you get back to sine x. So that is basically how you would do this sort of a problem. So now let's get to the actual thing. Okay. Alright, so we have sine x dx right over here, from negative pi by 3 to pi by 3. So we already know that this will be negative cosine x. We don't add the plus c because we do have bounds. And this is from negative pi by 3 to pi by 3. So in order to get from here, you just have to know this formula, which is f of b minus f of a. And what this says is that the f is this function, which is negative cosine x, and the b will be this pi by 3, f again, and then a will be this negative pi by 3. So the whole thing goes f of x a to b. So you just plug in b, and then you plug in a, and then you get that. So that's basically how you do that. So you'll have negative cosine x pi by 3 to negative pi by 3. So we can do negative cosine of pi by 3 minus, because of this part of the formula, negative cosine of negative pi by 3. Okay. Minus minus becomes plus, obviously. So negative cosine of pi by 3 plus cosine of negative pi by 3 is um our main answer, or we're getting close to the answer now. So now let's explore what this part of the equation actually means and how we will be solving it. So in order to do that, we'll have to take a look at the trig table. So let me just draw that. Or not the table, I mean the graph. X, Y, X, Y. So this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Right? We already know that much. So in quadrant 1, we know that both the cosine and the sine are positive. In quadrant 2, the cosine is negative and the sine is positive. In quadrant 3, both are negative. And in quadrant 4, the cosine is positive and the sine is negative. Oops. Right? And as in sine, I mean SIN. So, knowing this information, cosine of pi by 3, or we know that this is pi by 3 and this is negative pi by 3, right? And pi by 3 is basically 60 degrees in degrees, from radians to degrees. And the formula for that is, I'm just going to write that here. So if you have degrees and you want to go to radians, just multiply the degrees by pi over 180, and then you get radians. And then if it's radians and 2 degrees, you multiply by 180 over pi, because of just remember this one formula, and then with algebraic manipulation you can find the different formula for that. So you know all of this stuff, right? But you don't really care about the degree, as long as you know that the cosine of 60 degrees, or pi by 3 radians, is 1 over 2. So both of these will be positive 1 over 2 because of the cosine for both of these areas is positive. So we'll have a negative 1 over 2, the negative coming from this, plus 1 over 2. And our answer for this problem will equal 0. And this is how you solve this problem. We'll be going more in depth into these. And this is question number 1. Alright guys, let's move on to the next problem. So now we're going to do a little bit more complicated problem that is pretty easy if you know the concept behind it, as always. Right? So it's going to be integral from 0 to 5 of absolute value of 2x minus 6 dx. Okay? So at first sight, this may seem like a very complicated problem because of the absolute value, but trust me, it isn't that complicated. So in order to do this problem, we're going to revisit the piecewise function. F of x is equal to two functions. So in order for us to, so one of them will be negative 2x plus 6. The other one will remain 2x minus 6. And in order to find the bound, so how did I get this negative 2x plus 6? I just made negative of 2x minus 6, where I got negative 2x plus 6. And you do that because you're looking at both sides. You're not just looking at one side. So the first side would be this, and then this is the second side, which is the one that is more negative to the you'll see what I'm talking about. So let's say that we have 2x minus 6. So in order to find the bound, we would set 2x minus 6 equal to 0, 2x equal to 6, x equal to 3. So I said equal to over here, but it's not actually equal to, it's actually greater than or equal to. So over here, x will be greater than or equal to 3. And then here, it automatically becomes x is less than 3, right? Yeah. So this will be the negative alternative for negative 2x plus 6. And this will be the positive side of the scale for 2x minus 6, which is the original function. So just keep that in mind, and in order to find the bound, it's just doing this, and you will find the bound there. So let's get rid of all of this. Right, let's get back to work on the original problem. So we have this, and we know that we can't have, so we have like a small like intersection, I would say, at x equals 3, right? So how do we proceed from here? So we can just say that negative 2x plus 6 goes from 0 to 3 on the in this scenario, and then 2x minus 6 takes it from 3 to 5 in this scenario, because we're going from 0 to 5, right? So this is as simple as going from 0 to 3 of negative 2x plus 6 dx, and then let's get rid of this area right here. Messed up. Alright, get rid of that. And then you can add this right over here. Then from 3 to 5, as you can see, this is greater than or equal to 3. We can do 2x minus 6 dx. Okay, so we have negative 2x plus 6 for this side from 0 to 3, as we see over here. Negative anything below 3, and then our initial, our a is going to be 0, and this is our b, which is 5, and this would be our c, which is 3, which we got by saying this equation equals 0, right? Get rid of that. So now let's try to do this one. So this would be negative x squared, because it's x squared raises power by 1. You divide by 2, 2 and 2 cancel out. 2 cancel out. So these 2 cancel out. You have this square, which carries on over here. Plus 6x from 0 to 3. Plus 2x minus 6. Same thing. go here, cancel that out. So we have positive x squared minus 6x from 3 to 5. And then we have all that, right? So 3 times 3 is 9, negative 9, plus 6 times 3 is 18. And then we already have a 0, so 0 is 0. You know, it doesn't really matter, we don't have to calculate that. So this comes out to be positive 9. So we'll keep that intact, add the plus sign here. 25 minus 30, which is going to be negative 5. And then 9 minus 18, which is going to be negative minus 18, which is going to be negative 9, right? So it's negative 5 minus negative 9, because f of b minus f of a, so it's negative 5 plus 9, which is 4. So we have 9 over here and we have 4 over here. So our answer to this equation is going to be 13. Because 9 plus 4 equals 13. And this is how you would solve an absolute value function or integral with an absolute value. Right. And next we'll be looking at some, this is problem number 2. Next we'll be looking at some indefinite integrals. So yeah. Alright guys, we'll now be doing a short review study session. This is going to be about inverse trig. Yeah, so let's do it. So we're going to start by saying that derivative of sine inverse x is going to be, or no, let's do sine inverse u, because that is a much better. Sine inverse u is equal to u prime over square root of 1 minus u squared. Okay. Now the derivative of cosine inverse u is going to be negative u prime over the square root of 1 minus u squared. Now, one thing you notice here is that sine is positive and cosine is negative. So that's one observation I can make. And then, so the first one is sine is positive, cosine is negative. The second observation I can make here is that on the bottom, we have a square root in denom, and this square root is like, well, these observations are going to help us remember which formula is which, because we're going to have to do this for all 6 inverse trig functions. So remember that there's a square root in the denominator, and that in the square root we have 1 minus u squared. And then the third observation we can make is that on the top we have du by dx right here. Well, d by dx. Yeah, so this would be, yeah. So in the, we have like a u prime in the top, and then, so it would always be u prime over something. okay? No matter whether it's sine or cosine. So these are the three observations we can make for the inverse of sine and cosine. Let's see if we can fit cotangent and tangent here, so that we can also observe these in relation to the ones up here, sine and cosine. So tangent is going to be u prime over 1 plus u squared, and cotangent will be negative u prime over 1 plus u squared. So what are the observations we can make with tangent and cotangent? So unlike sine, so observation 1, unlike sine and cosine, there is no square root in denominator. So we don't see a square root in the denominator in tangent and cotangent, but in sine we do have a square root. So that will be one way to remember. Like, just remember that square root in sine and cosine, no square root in tangent and cotangent. And observation number 2 is that tangent is positive, but cotangent is negative. So just like sine and cosine, sine is positive, cosine is negative. We have tangent is positive, cotangent is negative. So we must remember that. And then observation number 3 is that there's also u prime in the numerator. So, u prime in the numerator. So, as you will see when we go to secant and cosecant, this u prime in the numerator never changes. It will always remain the same because, okay, so we'll do the proof later, but for now just remember that the u prime will always stay in the numerator. So let's get rid of everything here. Alright. So now let's do secant and cosecant. So the derivative of secant inverse u, my bad, will be u prime over the absolute value of u, and then we have a square root u squared minus 1. Now, and then cosecant, cosecant inverse u cosecant negative u prime over the absolute value of u, and then u squared minus 1. So this cosecant, this secant, and once again we have a negative for cosecant, and we have a positive for secant. So the positive ones will be tangent, sine, and secant, and the negative ones will be cotangent, not secant, cosecant and cosine. So that's like one good way to remember the signs, observations for this. So we can observe that we have a square root in the denominator, like sine and cos. But one thing in both, obviously, in both of these. But one thing that is surprising is that in this inverse sine denominator, we have 1 minus u squared. But in secant and cosecant, we have u squared minus 1. So you must remember that order does matter no matter what happens. So never confuse this order. Like always, like memorize this as much as possible, and it will actually help you a lot when you're going to like take a test or something. So let's get rid of this. Okay. So order does matter. Don't forget that. And then, so we have covered all of the derivatives of inverse trig. Second observation I can make is that secant and cosecant are the only ones to have an absolute value of u in the denominator. So this is only for secant and cosecant. The third observation is obviously that there's a u prime and in the top, in the numerator. So never forget that there's always u prime no matter what happens, no matter which one of these we're talking about. Secant and cosecant are the only ones that have an absolute value in the denominator. Remember this positive and negative chart. And remember that order does matter for secant, cosecant versus cosine, sine. Because in cosine, sine, we have square root of 1 minus u squared. And in secant, cosecant, we have u squared minus 1. So don't forget that. So now let's do a couple integrals of these. Get rid of the whole scene we have going on here. Okay. So do the integral of du over square root of a squared minus u squared. Alright. So we have du of square root of a squared minus u squared. Du over squared, right? This is going to be equal to arc sine or sine inverse of u over a plus c. So let's suppose u was like x and then a was like 1 minus x squared. This would just be sine inverse of x over 1 or just x plus c. It's pretty simple. Just remember that like squared and then you just have to take one of these. Don't take the full square and then put it here. You don't want to put the square there. And then for this, remember to take the square root. Square root of 1 is just 1, so that's why I could put that in. So don't forget that for this thing. Right? So that is sine. Now let's go to cosine. So in the beginning we saw that sine and cosine are literally the same, except in cosine we have a negative. So if you see a negative minus u squared, So if you see a negative here or a negative inside, don't confuse that for two different negatives. It's just one negative. If you see one negative, you know that it's going to be cosine inverse u over a plus c. Alright, let's go on to tangent. So tangent is just the same thing, except remember when we observed that in the derivative of arctangent we don't have a square root in the bottom? Well, we don't have a square root here either. So no square root, and if you see there is no square root, it will be as simple as 1 over a arctangent or tangent inverse u over a plus c. And then for cotangent, if you see a negative, it's 1 over a cotangent inverse u over a plus c. Which is pretty simple. Keep that in mind, you know. Yeah, so let's clear this space up. Alright. So now we have secant and cosecant, arcsecant, arccosecant, which will be integral of du over u divided by the square root of u square minus a square. And you can immediately see that you have a u in the bottom, then you have u squared minus a squared. In the sine one, this is the sine by the way. In the arc sine one, we had du over square root of a square minus u squared. But in this one, we have it changed. So order does matter. And if you observe carefully, you'll see that this is the same as the derivative that we took. So d by dx of sine inverse u, it was equal to u prime over square root of 1 minus u squared. And then d by dx of not sine secant inverse u equals u prime over u, and then square root of u square minus 1. Right? So we had u square minus 1 over here, and then we have 1 minus u square over here, and we also have this thing, but the one thing that stays the same is the u prime on the top, and the sine actually, because remember both sine and secant are in the positive chart. So let's get rid of that. So we have that, and then we have this. So this is just going to be 1 over a arcsecant absolute value of u over a plus c. And I'm sorry if I forgot the plus c in the other examples, but never forget the plus c. If you forget the plus c, you're basically just not going to get, because if you have a definite integral and you forget the plus c, it means that you're not considering a family of functions. And I'm not really sure if I forgot the plus c or not, but just remember never to forget the plus c. In an indefinite integral, however, you don't need this. You would just close it off right here with the bounds, and then you would plug it in and solve. And yeah, that would be pretty easy. But you know, plus c for the indefinite ones, and no plus c for the definite ones. So that is that. And then we have negative. If you have negative, it would just be arc cosecant, right? same thing. So I think that about concludes this part. So I think that about concludes the video, to be honest. Thank you guys for watching. Make sure to like, subscribe, and comment. And I'll see you guys in the next one. And we'll be proving the we'll be proving the arctangent and the arcsecant formulas. Arcsecant x, arctangent x, and we'll try to prove some other stuff. And you know the one thing I like about math is that if you follow the proofs, you'll actually end up you'll actually end up understanding the concept better than if you did not know the proofs. So that's like the one thing that I love about math, is that there's proof for everything. Like there's proof for everything in the universe, and then you can always have you'll always come to some conclusion under that proof. So I'm going to focus on the proofs in the next video. But for now, I think I'm pretty tired and I need to sleep. So I'll see you guys in the next one. Have a great day, guys.